All right. Hello, everyone. So today we're going to begin on our final physics club meeting of the year, in which we're going to complete our quantum mechanics unit. But first, let's look at some announcements. So for the officers for next year, we created an informational video, as well as the physics club officer form. And so here we have, if you're interested in applying for the officer position, be sure to watch this video, as well as look through the form. There's like a name, grade, and officer position, as well as a few questions about becoming the officer for next year. And so now let's continue with our discussion of 1/2 spin states. And one more thing, we have an update to our V Club. So check out our V Club's page when you receive the time. So for 1/2 spin states, we will begin with a system of two spin 1/2 particles, which are our electron and our proton. And they actually have this hyperfine interaction because of the mass of the proton, which is 2,000 times larger than that of the electron, which means that the magnetic moment, which is inversely proportional to the mass, will be 2,000 times smaller for a proton than the electron. And so this is the hyperfine interaction because of the small scale. And next, we'll look at some mathematical ideas. So we need to construct basis state for our 1/2 spin system. And so these are basically the basis vectors in quantum mechanics. And you can see these four basis states expressed as a direct product over here, which will be helpful in the matrix representations. So try to keep these are basically like our unit vectors, essentially, that we're working with, our basis states. So just keep these in the back of your mind as we proceed. Next, we'll discuss computing a Hamiltonian, which will later be useful in our Schrodinger equation. So here A is a constant with dimensions of energy, and we're familiar with H bar already from previously. And we also have S1 and S2, which are our angular momentum operators. And so now we'll simplify by recognizing the two S1 dot S2 right here. We can simplify this as follows, using this S1 plus, S1 minus, S2 plus, and S2 minus notation, and some substitutions. And this is how we're going to compute our Hamiltonian here. And so here you can see that we use the dot product at the top. This first line is the definition of the dot product, right? In which we're multiplying out the components of the vector. And here we just use the definitions below to make the simplifications to these quantities. And you can check that this works by substituting this properly. And so we can use our Bra and Ket vectors in order to compute the components in our Hamiltonian matrix. So you can see, what if I want to compute like a diagonal element, like 1 H hat 1, right? 1 Hamiltonian 1, and to compute this, we can use our substitution of our definitions of unit vectors. And so in this way, we can compute and see that it's A over 2. Similarly, you can take like a non-diagonal element like this 3 Hamiltonian 2, and we can substitute again our definitions. So using the definitions, we can compute different quantities in terms of our constant of units of energy. And so if we work through all of these computations, we get this Hamiltonian matrix over here. And this is basically just by doing component by component. You have 1, 1 here, 3, 2 here. And we just go component-wise and we compute this Hamiltonian here. So that was how we compute the Hamiltonian. And we mentioned that we were doing this to plug it into our time-independent Schrodinger energy eigenvalue equation. Here you have the Hamiltonian matrix on the left. And here you can see how we're expressing our eigenfunction in terms of different basis states, 1, 2, 3, and 4 that we had from before. And we also have this energy eigenvalue. Now, if you remember, we were discussing this last time with our energy eigenvalues, in which you have determinant of A minus lambda I is equal to 0, where lambda is eigenvalue and I is the identity. And this is basically just showing that computation, where you have A over 2, a minus E, and then you take like every other element on the diagonal, and you subtract out the eigenvalue. And so if you remember like a linear algebra, right, some of the pre-calculus skills, right, we can take our determinant of this matrix. Now that we've subtracted our eigenvalue E from each of these diagonal elements of the Hamiltonian, we will now compute the determinant. And using that, we'll get our eigenvalues, which will be E is equal to A over 2 with multiplicity of 3 in the final equation, which makes 3 eigenvalues. And then E is minus 3A over 2, which is an eigenvalue as well. And this is very important because now we can identify our eigenstates in our system. And so we have our eigenvectors and our eigenstates by using some back substitution. And you can see those over here, where we're taking our eigenvectors, and you can interpret those into eigenstates. This 1, 0, 0, 0 is this plus z state. Similarly, this 0, 0, 0, 1 is a minus z state. And here you can see different interpretations because we're just using the eigenvector here, the components of the eigenvector to translate into eigenstates, as well as our 1, 2, 3, 4 basis vectors that we had before, which are very important in defining our system. Next, we'll think about quantum entanglement and John Bell experiment. So we have the EPR paradox, in which you have a spin 0 particle decaying into 2 spin 1/2 particles. And by conservation of angular momentum, there should be 0 relative orbital angular momentum between these particles, and spin should be measured oppositely. Also, measuring one particle will instantly determine the measurement with respect to the other, right? So if you measure one like spin up, then the other is instantly determined to be spin down, right? And we note that because of our Stern-Gerlach experiment, we have the two possibilities of spin up and spin down. But this is kind of counterintuitive because you can put those particles at a very high distance, right, between each other. And so it would seem as if this information has been kind of communicated faster than the speed of light because you can put them at like two ends of the universe, right? And then you take like one measurement and the other measurement is instantly determined. And so there's this very counterintuitive nature of the EPR paradox. Now we'll look at a video from Veritasium for a few minutes in order to learn a bit more about the EPR paradox and how John Bell's experiment was used to resolve the EPR paradox. I'll optimize this for video sharing, I think.
Which could be light years away. It's as though the choice of the first measurement has influenced the result of the second faster than the speed of light, which is indeed how some theorists interpret the result. But not Einstein. Einstein was really bothered by this. He preferred an alternate explanation, that all along the particles contained hidden information about which spin they would have if measured in any direction. It's just that we didn't know this information until we measured them. Now, since that information was within the particles from the moment they formed at the same point in space, no signal would ever have to travel between the two particles faster than light. Now, for a time, scientists accepted this view that there were just some things about the particles we couldn't know before we measured them. But then along came John Bell with a way to test this idea. This experiment can determine whether the particles contain hidden information all along or not. And this is how it works. There are two spin detectors, each capable of measuring spin in one of three directions. These measurement directions will be selected randomly and independent of each other. Now, pairs of entangled particles will be sent to the two detectors, and we record whether the measured spins are the same, both up or both down, or different. We'll repeat this procedure over and over, randomly varying those measurement directions, to find the percentage of the time the two detectors give different results. And this is the key, because that percentage depends on whether the particles contain hidden information all along or if they don't. Now, to see why this is the case, let's calculate the expected frequency of different readings if the particles do contain hidden information. Now, you can think of this hidden information like a secret plan the particles agree to, and the only criterion that plan must satisfy is that if the particles are ever measured in the same direction, they must give opposite spins. So for example, one plan could be that one particle will give spin up for every measurement direction, and its pair would give spin down for every measurement direction. Or another plan, plan 2, could be that one particle could give spin up for the first direction, spin down for the second direction, and spin up for the third direction. Whereas its partner would give spin down for the first direction, spin up for the second direction, and spin down for the third direction. All other plans are mathematically equivalent, so we can work out the expected frequency of different results using these two plans. Here, I'm visually representing the particles by their plans, their hidden information. With plan 1, the results will obviously be different 100% of the time. It doesn't matter which measurement directions are selected. But it does for particles using the second plan. For example, if both detectors measure in the first direction, particle A gives spin up while particle B gives spin down. The results are different. But if instead detector B measured in the second direction, the result would be spin up, so the spins are the same. We can continue doing this for all the possible measurement combinations, and what we find is the results are different 5 out of 9 times. So using the second plan, the results should be different 5/9 of the time. And using the first plan, the results should be different 100% of the time. So overall, if the particles contain hidden information, you should see different results more than 5/9 of the time. So what do we actually see in experiment? Well, the results are different only 50% of the time. It doesn't work. So the experiment rules out the idea that all along these particles contain hidden information about which spin they will give in the different directions. So how does quantum mechanics account for this result? Well, let's imagine detector A measures spin in the first direction and the result is spin up. Now immediately you know that the other particle is spin down if measured in the first direction, which should happen randomly 1/3 of the time. However, if particle B is measured in one of the other two directions, it makes an angle of 60 degrees with these measurement directions. And recall from the beginning of this video, the resulting measurement should be spin up 3/4 of the time. Since these measurement directions will be randomly selected 2/3 of the time, particle B will give spin up 2/3 times 3/4 equals half of the time. So both detectors should give the same results half of the time and different results half of the time, which is exactly what we see in the experiment. So quantum mechanics works, but there is debate over.
All right. And so that was our video. And so hopefully you were able to see how it's not true that there was actually some hidden information there, and that quantum mechanics does work, as Veritasium concluded. And we also note that we were able to use the mathematics to get a little bit more of an idea of how to interpret and how to interpret our spin system, our 2 1/2 spin system. Next, we'll continue with scattering in quantum mechanics.
Okay, so now we're going to go into scattering. So basically, scattering is just collisions between particles. So if you just have like two particles approaching each other, they're going to collide and then scatter off at some angle. And so I've got this picture of Rutherford's gold foil experiment because that is actually an example of scattering. So he was shooting a beam of alpha particles into the sheet of gold foil. And of course, some of them were undeflected because they passed through the empty space in the atom. But some of them scattered off at an angle. And so what was happening here is we have the scattering process between alpha particles and the atomic nuclei. And so by doing a scattering experiment, we were able to deduce information about the internal structure of the atom. So scattering is actually very useful. You can go to the next slide. Yeah. So how do we look at scattering? A very easy way to depict scattering processes are with Feynman diagrams. And so these were invented by the legendary physicist Richard Feynman. And he basically made it so that basically anyone can look at these diagrams and know what's happening in the process. So for example, let's look at this process. So we have an incoming electron here denoted by E minus. And then we also have an incoming positron denoted by E plus because it's the antiparticle of the electron. And so the arrow on this positron may make it look like that it's actually going outwards, but that's just because it's an antiparticle. Whenever you have an antiparticle, this arrow is going to be in the opposite direction of the direction that it's actually going. So this is an incoming antiparticle, an incoming positron. So we have this incoming electron and an incoming positron, and they're going to combine into this photon here, which is denoted by gamma and this squiggly line. And then that photon is going to come to a vertex here and then split off into a quark and an antiquark. And this antiquark is also going to emit a gluon, which is denoted by G and this coily line. So if you go to the next slide, we have more examples of Feynman diagrams. So let's look at this first one on the left. So here we've got two incoming gluons, which are going to combine into one virtual gluon. And then that gluon is going to split off into a bottom quark, which is going to emit another gluon, and an anti-bottom quark. And so in this process, we just have two gluons going to a quark-anti-quark pair and another gluon. In this interaction, we're starting with an incoming neutrino. Whenever you see a V, that is denoting a neutrino. And so we have an incoming neutrino, and it's going to come to this vertex, and it's going to emit a W boson, which is one of the intermediating particles for the weak force. And then the neutrino is going to turn into an electron. So in this process, we're going from a neutrino to an electron and a W boson. And then in this final process over here, we just have two electrons coming in. And then this first electron is going to emit a photon and then turn into this final electron. And then this other incoming electron is going to absorb that photon and then turn into this outgoing electron. So we just have electron to electron scattering in this example. So if you go to the next slide, then we can actually use these things called Feynman rules to translate Feynman diagrams into equations, which we can then use to find expressions about what is going on in the process. So there are different sets of Feynman rules for different theories. So if you go back to the previous slide real quick, so in like this first one, what we have going on here is gluons and quarks. And so that's going to be the strong force. And the theory that describes the strong interaction is quantum chromodynamics. So for this process, we would use the Feynman rules for quantum chromodynamics. In this process, we have weakly interacting particles. So we're going to use the Feynman rules for electroweak theory. And then in this process, we just have particles that interact with the electromagnetic force. So we're going to use rules from quantum electrodynamics. So you can go back to the next two slides now. And so once we apply whatever Feynman rules are applicable to our theory, our process, and you simplify that expression using a variety of complex rules and strategies, you obtain this scattering amplitude, which is denoted by script M. And so this scattering amplitude is a probability amplitude. It is used to find the probability of how the particles will scatter. And if you go to the next slide, the quantity that is actually going to tell us that is the differential cross-section. So the differential cross-section d sigma over d omega gives the probability that a particle passing through the area sigma before scattering will end up in the solid angle omega after scattering. And so we've got this expression for the differential cross-section over here, and we can see that we can obtain it using the scattering amplitude multiplied by some factors. And so if you go to the next slide, we have a pictorial representation of what the differential cross-section is. So here we've got the differential cross-section d omega. We've got this area here that the beam of particles are going to pass through. And then those particles are going to scatter off, some of which are going to scatter into the differential solid angle d omega. And what we mean by solid angle is basically just the three-dimensional equivalent of an angle. And so that's a pictorial representation of the differential cross-section. And so if you go to the next slide, then we have another definition of the differential cross-section. So we have that it is also defined as the number of particles scattered into that solid angle d omega per unit time divided by the number of particles going through per area per unit time. And so if we just cancel out these units of time, we can see that the differential cross-section works out to be in units of area. And if you go back to the previous slide real quick, then we can see in that image that the differential cross-section is just this cross-sectional area right here. Okay, so you can go to the next two slides now. So now we're going to look at, oh my gosh, I only have 5 minutes. Okay, so we're going to look at an example of quantum electrodynamics, which is the theory of particles that interact with the electromagnetic force. So like electrons and muons and photons and stuff. So you can go to the next slide. So these are just the Feynman rules for quantum electrodynamics. I think we're going to skip going through these entirely just for the sake of time, so you can go to the next slide. But the process that we're going to be looking at is this dude right here. So we have going on here is we have an incoming electron right here and an incoming positron, and those are going to combine into a virtual photon. And then that photon is going to split off into an outgoing muon and an outgoing anti-muon. So that is the process that we're going to be looking at. And then in the next slide, we see that we can use the Feynman rules for fermions and QED to translate that into an equation for the scattering amplitude. So 1 second, let me move my stuff around. Okay, so let's try to translate this into an equation, but really quickly. So first we have our incoming positron, which is an incoming anti-fermion. And so we're going to use this factor of V bar S of P. So we're going to see that right here in our equation. And then we have the vertex right here. And so we can see in the Feynman rules for QED that an interaction vertex contributes a factor of IQ gamma mu or negative IQ E gamma mu, which we're going to put right here. And then next we have our incoming electron, which we can see is denoted by this US of P right here. And then so these two particles are going to come together and turn into the virtual photon. And we can see in the Feynman rules for QED that an internal photon line contributes a factor of negative IG mu nu over K squared plus I epsilon. And so we've got that right here. And then the virtual photon is going to split off into the muon and anti-muon. So first we have the outgoing anti-muon, which we can see here is going to be U bar S of P. They meant to write outgoing anti-fermion because whenever you see like a bar, that denotes an antiparticle. So this is an outgoing anti-fermion. And so that's going to be right here in our equation. And then we have the interaction vertex, which we saw before. That's going to be another factor of negative IQ E gamma nu. So we've got that right here. And then we finally have our outgoing fermion, which we can see here is going to be VS of P right there. So using the Feynman rules, we have directly translated this pictorial representation that anyone can interpret into like this complicated mathematical equation. Okay, so if you go to the next slide.
I think this is the last slide.
Oh wait, oops. So I thought I had another slide after this, but I guess not. Maybe that's good because we're running out of time. But so basically, using these Feynman rules, we have translated this Feynman diagram into this complicated expression. And we're not going to go through the process of simplifying this expression to get the differential cross-section because I think simplifying this expression would take like an hour. But after we have done that, we would just use that equation from before, that d sigma d omega equals the amplitude squared over 64 pi squared or whatever it was. And so we could use that to obtain the differential cross section, which is going to give us the probability of how these particles are going to scatter. So that was an example of quantum electrodynamics and a little introduction into scattering processes. So that's going to be it for today and it for the year, which is really sad, but we definitely had a lot of fun doing physics club this year and we hope you did too. So yeah, thank you for coming.
All right, thank you so much, everyone. The mathematics is very important for grasping the nature of quantum mechanics. And so we thank you for joining us throughout the year, everyone. and apply to an officer if you're interested for that.